Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 5.2.3. This is titled Compound Independent Events. And I'm pretty sure we should probably front load a few terms here. For instance, independent events. What's the difference between a dependent event and an independent event? That's what we want to make sure that we understand, the differences between those two types of events. And so let's jot down, some of this vocabulary. First of all, we need to know what an event is. So let's refresh our memories. An event or events are one or more results of an experiment. So like when you roll the die, that's an event. Okay, if you were to roll two different die, like one person rolls one and another person rolls another, each one of those are events every time you roll the die. Dependent events are the types of events where one outcome affects another. So if you think about that rolling of the die, if I roll a die, does my number affect your outcome in any sort of a way? If it did, then that would be considered dependent events, where one of them was affected by the other. But that particular example does not fit in with dependent events. Those would be what we would call independent events, where one outcome has absolutely no influence and no effect on another outcome. So throughout this lesson, we're going to look at some situations that are dependent, and we'll look at some other situations that are independent. And so by the end of this lesson, our goal is to be able to do a little bit more complex probability solving and be able to determine whether or not a situation or an event would be considered dependent or independent. When you studied probability in earlier lessons, you focused on probabilities of single events, like drawing a card from a deck or picking out a cube or a bead or a marble or whatever from a bag. You also examined probabilities of either one thing or another thing happening. Okay, so either one or another of two events occurring. For example, either winning the lottery ticket or cash, or either drawing a king or a queen, or my favorite situation is, when you've got a spinner that has different colors. You've got a certain probability of landing on each color, but what if you could land on blue or red? How did you calculate the probability of blue or red? Well, we added together, right? And so in this lesson, we're going to start thinking about some independent events where one does not affect the other, and we're going to focus on the word and. Okay, so in this lesson, you will begin to investigate when one and another event both occur, such as flipping two coins or spinning the spinner multiple times. Throughout this lesson, use these questions to help focus our discussion. Does the result of one event affect the other? Right? That's how we determine whether or not they're dependent or independent. And then how many possibilities are there? All right, in chapter 1, you met Chris and her older sister, Rachel, who made a system for determining which one of them washes dishes each night. Chris has been washing the dishes much more than she feels is her fair share. So she has come up with a new system. She has proposed to Rachel that they get 2 coins. And each day, she and Rachel will take and flip the coins at the same time. If the coins match, Chris washes the dishes. If they do not match, Rachel washes the dishes. Rachel thinks this is a great idea and that her little sister is being very silly. She thinks to herself, since there are 2 ways to match coins, either getting heads and heads or getting tails and tails, but there's only one non-match way where you would just get a heads and a tails, then Chris will still end up doing the dishes more often. Ha, 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 ha. So, do you agree with Rachel? Does it seem like Rachel is making sense, or is Chris correct? And this really is a more fair way of determining who will wash the dishes. I guess that's an opinion piece on your part, but I'll kind of share what I was thinking here. It seems like, no, there are two ways to match and two ways not to match. Seems like that would be the case. So does it matter if they flip the coins at the same time? Does the result of one coin flip depend on the flip of another? So let's think about that for a second. If two people are flipping coins, one can flip first. Will that have any effect on the other result of flipping that coin? Or would it be better if they both flipped at the exact same time? Does it make any difference? Does one affect the other at all? And the answer to that is no, it doesn't. One of them does not affect the other in any way, shape, or form. Each flip is independent of the other. Okay, so what we need to do now is organize all of the possible outcomes of their flips. It says here, use the word and when you're talking about both this and that occurring. So when we actually write the probabilities and write out the explanations, we'll make sure that we include this terminology. So what I'd like for you to do is set up a table. And we're going to have Chris, who will be number one, and Rachel, who will be person number two, coin number one, coin number two. And we're going to look through all the different possibilities of combinations here of flipping a heads and a tails. So go ahead and pause for a second to get this organized. You just write it exactly like I've got it, and then unpause when we're ready to explore all of our different combinations, all of our different outcomes. All right, so let's be organized about this. Let's not just do this randomly. Let's choose the first person, which we're going to have be Chris, because I wrote Chris on the left. And let's suggest that Chris flips ahead the first time she flips the coin. And let's say that Rachel also flips ahead. Who wins in this situation? Remember, if the coins match, Chris washes the dishes. So the coins match, right? So we're going to say this would be for Chris. Actually, I wrote number one and number two. Let me just write down number one. That's Chris. Okay. Now let's say that Chris flipped heads again, but Rachel flipped the tail. So wins in this situation, they don't match. So it means that Rachel, number two, Rachel would win that one. What if when Chris first flipped, it was a tail and Rachel got a heads? Well, that would mean Rachel would win again. And the last scenario involves both Chris and Rachel getting tails. And they match, which means that Chris would be the winner. So what do you notice about the outcomes? This is the theoretical probability, right? We're not doing a simulation and we're not doing an experiment, which we could, I suppose, if we really wanted to. We could go onto the online book and play around with a little flipping of the coins and see how often each one had to do the dishes. In fact, let's go ahead and do that right now. Let's see, we'll do like 20 simulations and see who has to do the dishes and see if it ends up being about 50% for each one. Okay, so let's go. Maybe I better close this guy's down and go to the next page. That can be where I do my record. I'm going to do this guy like that. Here we've got a heads and well, two different coins, right? And by the way, to get there, just like all other situations, just go to the online book, find the online tool. It's the student tool for problem number 43. When you click on it, this comes up. Okay, so I'm going to go ahead and let's see, we've got Chris and we've got Rachel. And every time they match, Chris is the one who does the dishes. When they don't match, we'll put a tick mark for Rachel. And I'll start by doing it 10 times, then I'll do it another 10 times for 20 to see how close we get to 50%. So let's go ahead and check this out. They do not match, so that is Rachel. They match, that is Chris. They do not match, that is Rachel. They match, that is Chris. That is a non-match. That is a non-match. That is a non-match. That is a match. That is a non-match. And that is a non-match. So, according to this, Rachel has to do it 70% of the time. which that's, once again, it's a simulation, it's experimental probability. They don't always match theoretical. Let's do it another 10 times and see if this gets closer to the actual 50% that it's supposed to be. So I'll make a new row. So there's a non-match. It's not looking good. There's a match. There's a non-match. There's a non-match. Oh, this is not looking good for our theoretical probability. There we go. We're starting to catch up a little bit, but I don't know if we're up. Oh, we're starting to catch up a little bit. There is a non-match. So that's 8. There's 9. And there's 10. Well, that was 60% and over. So it did get closer to the 50%, but still overall, what do we have here? 1, 2, 3, 4, 5, 6, 7 out of 20 is 35%. That is not what it's supposed to be. It's not supposed to be 35, 65. Right, the 13, there's a 13 for Rachel. She had to wash dishes 65% of the time, but it did get closer. And I imagine if we did it 40 times, if we did 100 times, if we did 1,000 times, it would eventually get 50-50. So what do we have here for our final? It says, actually, let me take a peek at it for a second. Okay, so I think I'm just going to do a reveal here. It says, what are all the possible outcomes when the girls flip their coins? Organize the possibilities. Use the word and when you're talking about both one thing and another thing occurring. So for these are the matches, right? This would be if Chris would win. She would either get a heads and a heads, which is a 1/4 probability, right? The heads and a heads, that's 1 out of the 4 is 2 heads. And then 1 out of the 4 is 2 tails. So that is a 1/4 probability. Now it's kind of interesting because if you think about it, the probability of getting a heads alone is 1/2, right? And the probability of getting tails alone is 1/2. So you're getting a heads and a heads. We did not add 1/2 plus 1/2. We did something else with those probabilities to get 1/4. That's something worth exploring to see if that is a pattern and something for us to learn as a process for finding this kind of probability. And then the tails, one tails is 1/2. Getting another tails right after that is also 1/2, 1/2 and 1/2 making 1/4. What do you suppose we're supposed to be doing with those two probabilities when we're working with the word and? Something to explore. So the probability of a match happening, whether it's heads and heads or tails and tails, would be 1/4 plus 1/4, which is 2/4, which is 50%. Now for the non-matching. Heads and tails, once again, the heads is a 1/2 probability, the tails is a 1/2 probability, but there was only one situation out of the 4 where you got a heads first and then a tails. And then there was only one combination of tails first and then heads. Each one of those was 1/4. But when you add those together, because it's either going to be heads and tails or tails and heads, then that would be 2 out of 4, which is 50%. All right, everyone's rock, paper, scissors, right? Question for us is whether or not this is a fair game. Now, we assume it's a fair game because haven't you been taught since you were really little, since the first time you've played it, that this is a fair way to settle disputes? So we're kind of presenting it as a fair game. Now, for those of you that have never heard of rock, paper, scissors, here's the rules of how to play. At the same time as your partner, shake your fist 3 times and then display either a closed fist for rock, a flat hand for paper, or a 2 fingers extended for scissors, okay? Rock always beats scissors because rocks can crush a scissor. Scissors beats paper because the scissors can cut the paper, and the paper beats the rock because the paper can wrap itself around the rock, which always kills rocks. I don't know if you've ever tried that before, but promise you, you go take a piece of paper and wrap it around the rock, and the rock will die. So there you go. Something new is learned every single day. All right, so when you play it, I guess the key here of what would make this a fair game is, first of all, if you have to throw at the exact same time. And so that's why a lot of times when I have kids play it, I have them face their backs to each other so they can't see what the other person does. And then you have a third person who can witness what their throw is and then determine who the winner is. Okay, so let's go ahead and let's make another table here. For this table, person number 1, person number 2 has a choice of throwing either rock, paper, or scissors. So I'm going to go through a systematic process where I'm going to have the first person throw rock first. Actually, let me color coordinate. Oh no, I didn't want to do that. Let me color coordinate this. I think I said rock. First person's going to throw a rock. Then the second person, or then after 3 tosses, then they're going to do paper. And then after another 3, they're going to do scissors. Okay. And so it's number 2 that's just going to change every single time. So when it's rock and rock, who wins in that situation? It's a tie, right? So that means nobody wins. If it's rock and paper, paper beats the rock, which means the paper is going to win. So person number 2 in this scenario would win. And then rock, scissors, the rock crushes the scissors. So in this situation, person number 1 would be the winner. Now let's change it up to where person number 1 throws paper all 3 times here. Paper wrapped around rock, paper wins. So that would be person number 1 winning this time. Paper and paper, that's a tie. And then paper and scissors, the scissors cut the paper, so that means number 2 would win in this situation. And then if person number 1 throws, scissors all 3 times, scissors get crushed by the rock, so person number 2 wins this one. Scissors cuts the paper, so number 1, the scissors wins in this one, and then this one ends in a tie. What do you know about these results? Let's go ahead and answer some questions here. It says, while both players are making their choices at the same time, this game has 2 events. What are the 2 events? Okay, so if you remember, when we did our vocabulary at the very beginning, events are one or more results of an experiment. So what was happening? A lot of times people think that the events are either the paper, the scissors, or the rock. Really, the event in this case is each person is doing some sort of a throw, okay? So whatever their choice is, player 1's choice is one event, and player 2's choice is the other event, okay? If you and a partner are playing this game and you both go at the same time, does your choice affect the other person's choice? If you've got your backs to each other so you can't even see what the other person throws or shoots, are we shooting or are we throwing? I'm not sure what we're doing here. At any rate, does one affect the other? And if the game is played properly, then no, one would not affect the other. And that would make these what we would call independent events because one has no effect on the other. Okay? All right, so is this a fair game and how can you tell? Well, let's go back and look at our results. Please go through and analyze how many times did player 1 win, how many times did player 2 win, and how many times did they tie. Okay, go ahead and pause. I'm going to go ahead and pause. And you determine, answer that question. What's the question that we need to answer? Is this a fair game or not? How can you tell? Be ready to justify it with the numbers that we've got up here. Alrighty, so let's go ahead and take a look at this before we declare our answer. The probability of rock winning was 2 out of 9. The probability of paper winning was 2 out of 9. And the probability of the scissors winning was 2 out of 9. The probability of getting a tie was 3 out of 9. Actually, hold on for a second. I'm wondering if maybe I shouldn't declare our answers a little bit different from that table. Instead of number 1 and number 2, maybe, yeah, maybe I should do that. Let me go ahead and change these guys right here. Sorry, don't mean to bore you, but that's what we're doing. So in this case, it was rock and paper, paper won. In this case, rock and scissors, rock won. In this case, paper and rock, paper won. In this case, paper and scissors, scissor wins. In this case, scissors and rock. The rock wins, and scissors. All right, so I'm going to go ahead and highlight every time the rock wins, 1, yep, 2 out of 9. Every time that the paper wins, paper, that's 2 out of 9. Every time that the scissors wins, 2 out of 9. And then the tie happened 3 out of the 9 times. So maybe that's a better way of looking at that table. And that's what we get here. So I thought, okay, so there were 9 possible outcomes, 2 out of 9, 2 out of, so it looks like the tie is the most common outcome that you're going to have. But a tie, nobody wins, nobody loses, so that, that doesn't factor into whether it's a fair game. So whether you choose rock, paper, or scissors, you've got the same probability of winning for either one of those choices, which makes it a fair game. Now let's take a look at it. If we just exclude all the ties and we only focus on whether someone wins, that means there would be 6 total outcomes, and 2 of them are rocks, 2 are paper, and 2 are scissors. So each one of those represents a 1/3 probability of winning. So yes, each player has an equal chance to win. Okay, so imagine that 2 people, player A and player B, are playing rock, paper, scissors 12 times. If you expect to win 2 out of 6 times just by randomly playing and choosing, how many times would you expect player to win out of 12 times? And so that's where you do a little bit of proportional reasoning, right? So I probably should have left this as an X there so that we could set it up. If every 6 times you play, you're expected to win twice, then how many times would you expect to win if you played 12 times? And that's each person would win 4 times, and you'd probably expect to get 4 ties there as well. Now play it 12 times with a partner. Well, we're not actually going to do this. You could possibly run a simulation on that if you wanted to. But if you were in class and we were able to work with each other with our table groups and everything, which we're not doing right now because you're watching this on a video, we would be able to do this experimental probability. But if you have someone else at your home and you would like to go and play rock, paper, scissors and record the results after playing 12 times, then go ahead and pause, go do that, record the results, and then come back when you're done, okay? Otherwise, I'm going to pause, and then I'm going to unpause, so you can just see what the reveal shows. All right, so it says, how does the experimental probability for the 12 games that you played compare to the theoretical probability that each of you will win? Do you expect them to be the same or different, and why? Okay, so the answer is, if you're doing an experiment, it could be different. It doesn't have to always match the theoretical probability. The more times you play, however, the closer the experimental probability will come to the theoretical probability. So if you play 12 times, you might find that one person wins 9 times and the other one 3. But then you play 24 times and it gets closer and closer to an even split. If it's a fair game, every person should be able to win equally. So that would mean it would be 50% of the time one person wins and 50% of the time someone else wins. All right, now what we're going to do, this is the last problem, I'm pretty sure. For this problem, we're going to look at some different situations, and our goal is to determine whether or not the situation represents dependent events or independent events. Now remember, independent events means whatever you do for one event has no effect on the other. Okay? When it's dependent, the probability changes after you've done one of them. Okay? So let's take a look at this. Flipping heads on a quarter and then flipping heads on another heads. So whenever you flip a coin, does that affect any other flip of the coin? And the answer is no. Every time you flip the coin, it's an independent event. It has no effect on the next toss. So you could literally flip 10 heads in a row. Even though the probability is 50%, you could do 10 in a row. It's not necessarily always going to be heads and tails and heads and tails and heads and tails. So just because you flip a head the first time doesn't mean you're going to flip a tails the next time. So those are independent events. And then here it says choosing a jack from a standard deck of cards then not putting the card back into the deck. So remember, there are 4 jacks out of 52 cards. If on the second, this is number 1, that's your probability of pulling out a jack, 4 out of 52. If you do not put that card back in, you now only have 3 jacks and 51 cards. That is a different probability than this. This simplifies down to a 1 in 13 chance, where that simplifies down to 1 in 17. So that means that by pulling out the jack and not putting it back in, that affected the probability of your next draw, which means these are examples of dependent events. Then it says picking a blue marble from a big bag of marbles, then putting it back in, and then picking a blue marble again. Okay, so let me go ahead and change this over here. And let's pretend you've got, let's say you've got 5 out of 12 marbles are blue marbles. So you pull it out, and you got a 5 out of 12 chance of getting a blue marble. But then you put it back in. That means that the second time you draw out, you still have 5 blue marbles, and you still have a total of 12. So by putting it back in, that meant that every one of your probabilities would be exactly the same, making these independent events. And then rolling a 6 on a number cube 3 times in a row. Well, the first time you roll it, you got a 1 in 6 chance of rolling a 6. The second time you roll it, you've got a 1 in 6 chance. And then the third time, you've got a 1 in 6 chance again. It never changed the probability of rolling a 6 when you did it multiple times, which means that this is another example of independent events. All right? Alrighty, so I'm thinking this might be a good kind of a question for check for understanding. So go ahead and do your check for understanding, and then head over to your homework, and we'll check the homework tomorrow. Take care. Bye.
Hey, feeling good, like I should. When in dark, walk